Good afternoon, ladies and gentlemen. Welcome to another Heidelberg Joint Astronomical Colloquium. And this week we are extremely honored to have a very familiar but a very expert guest who will give the colloquium, namely Professor Ralph Pudritz from McMaster University. And Ralph will be familiar to a number of you because he's a regular visitor to Heidelberg, both at the Max Planck Institute for Astronomy originally, but more recently, often coming to the Institute for Theoretical Astrophysics. And Ralph did his PhD back in 1980 under Reg Fowlman at the University of British Columbia. And following that, he had a sort of whirlwind tour of some of the most prestigious institutions in North America and also in Europe, where he worked together with names such as Chris McKee, Colin Norman are two which come straight to the fore, before he was awarded an assistant professorship at McMaster University. And already at that time, he was working a lot in the field of star formation, during his time at McMaster, he rapidly, having been appointed in 1986, advanced to a full professorship in 1992. And then I think one of the main events after that was he was sort of hijacked into the sort of organizational side of Canadian astronomy. And I don't think it's incorrect to say that Ralph actually shaped a lot of the future and his input to the decadal survey made in Canada, not least promoting Canada's participation in ALMA and before that JCMT, which of course is so important to some of the topics which Ralph will be talking about today. And another big event was that Ralph was the founding director of the Origins Institute at McMaster, which is a transdisciplinary institute aiming to bring together people working in diverse fields such as high energy physics, cosmology, biology, planetary science, and of course, star formation. And it's those topics which today, star formation and planetary science, with emphasis on today's talk on planetary formation, which Ralph will be telling us about. So without any further ado, let's welcome Ralph, and we look forward very much to hearing what you have to tell us. Thank you.
Thank you very much. Can you all hear me back there? Okay, great. And thank you very much for that kind introduction, Richard. My topic here is going to be very broad, and I would like to jump straight into things by posing this general question. What are the connections between observed planetary properties, such as their radius, mass, their orbital dynamics, chemical composition, and planet formation? This is arguably one of the great drives in current astrophysics to make this connection between these formation conditions and planets as we see them. Now, the approach here is to note that the protoplanetary disk phase is probably critical to everything we want to do here, because in disks, we have planets migrating. Of course, their formation takes place largely while they're in the disk, not all of it. The composition is settled once the disk chemistry is decided, and a good part of the orbital dynamics of planets as they end up, not all, but a good part is established by migration and other properties while they're still forming in the disk. A key physical concept to keep our focus on during all of this complicated physics is angular momentum transport. Angular momentum must be conserved, and how it moves around affects most aspects of how planets form and evolve. In fact, the evolution of the disks in which planets form, the planet migration rates and their formation will be governed by angular momentum, how angular momentum is moved around in disks and bulk. And that brings up this important contrast here between two of the well-known and often worked on mechanisms of momentum transport and disk, which is a turbulent transport, versus the now becoming ever more interesting and popular disk wind transport. So let's dive in. So first of all, some observations. You all know this photo picture very well, but I'm just bringing up one of the key aspects of observations is that by observing transits of planets around a host star, we gain a huge amount of information about the apparent radius of the planet. As an example, if we do in this configuration, blocking the light of the background planet, depending upon the wavelength that we're looking at, the planetary size can seem to differ because different species in the atmosphere have different optical depths. And so the planet size seems to adjust according to the wavelength and the opacity transition we're looking at. Therefore, we can get a good deal of information about the composition of the planetary atmosphere by probing this configuration, light coming through the atmosphere to our observing source. We also can, of course, see planets, the emission of radiation from the planet atmospheres. So by these measurements, and together with the mass measurements we make by Doppler shift, we can go ahead and decide then the mass and radius and density of the planets. We can determine their orbital radii from the observations. And so now let's look at this from a population perspective. This very famous picture, this is how astronomers plot the data for the orbital semi-major axis of the planets and their planetary masses. Put this together a few years ago. The picture hasn't much changed, but you'll notice we've divided this into zones here for the planetary masses. Jupiter is 318 Earth masses, so that sits about here. So these are 10 Jupiters sitting up in here. 1 astronomical unit, you'll notice that there's a collection of Jupiter mass planets sitting at a couple of astronomical units. That happens to be the position of the ice line, more or less in our solar system, where water would condense into the solid phases. We do not see many planets, regardless of very sensitive surveys that have been carried out over the last few years. We do not see many planets out at large radii, but when we do, by selection effects, they tend to be quite massive and luminous. The bulk of planetary systems, about 65% of the planets we found, are in this super-Earth mini-Neptune sector shown down here, down below 1 astronomical unit. And so you see some sort of a separation of these populations, hot Jupiters, the warm Jupiters, the super-Earth and many Neptunes, a few planets out here. The zone beneath this, of course, cannot be really detected by the current instrumentation. So this is an observational selection effect here that cuts this diagram off in the obvious way. The other compilation data that we want to think about for this talk is the planetary properties, the mass radius diagram. This is the latest data I could find here, which have cleaned up the error bars substantially for planets out to 100 solar Earth masses. And we see that fitting lines here, planets which have a pure composition of iron, magnesium silicates, and pure water ice. You see that there's a change in planetary properties occurring at about 5 Earth masses, or a little bit shy of 2 Earth radii, in which suddenly things that seem to be fairly rocky, much like ourselves, are now dominated by planets. Take Uranus here. At the massive Uranus, you see that there's a wide variety of planets, same mass, but hugely different radial properties here. Whether this is different properties of gases or the ice phases is being currently investigated. So this great diversity having to do with variation of composition and no doubt equations of state matter in understanding these properties. You probably have all seen this picture. I won't dwell on it. This is a selection effect. We're looking at visible, bright, detectable planetary disks here shown by ALMA a few years ago, in which we see these regular structures and sometimes irregular ones here, kind of a frightening on this side of this disk. But the idea behind this is that perhaps it's planets that are responsible for carving gaps in these disks, but perhaps not always. We now have enough data to see what the distribution of disk properties is. And this latest compilation here by Nienke van der Mel and her collaborators, there's now about 700 disks and counting. These are arranged by her and her collaborators into different epochs here. This is given by looking at disks in these different cluster systems as an example. Orion, Taurus, and other well-known nearby molecular clouds whose age we more or less understand. And you see that the ring systems here, which are shown in red and blue, are a rarity. These systems happen to occur very infrequently. They're about 6% of this population of disks. Most of them are very compact. And that's a surprising result. Kind of naive theoretical calculations of the bygone era assume that collapses of large rotating objects, given the amount of angular momentum you saw in molecular clouds, would collapse as things like about 100 astronomical units, which would be like these guys. Disks are apparently much more compact than that. Models, if planets are responsible for carving these gaps by moving angular momentum around, then can we predict what kind of planetary masses we would find in this, say, HL tau system? That was the game plan of a number of different groups and a very active type of research going on in the field. And here for 3 different papers, you see an array here of models ranging from Dong et al., three Saturnian masses needed to rotate this ring system for a disk viscosity. So going forward, alpha here is the ratio of the turbulence speed to the sound speed squared. And it's a measure of how turbulent any system is. 10 to the minus 3 for this so-called turbulent viscosity. Here are models in which much lower viscosity is used and only a single planet is needed. So apparently, one needs to understand the physical properties of this, how turbulent it is, in order to make any predictions stick as to what you think the kind of planet is in there or not. Are these, in fact, produced by planets? There are calculations, which you putting magnetic fields into these disks as an example, you will find that flux will concentrate into alternate rings where the density gets slightly cleared out as magnetic flux gets concentrated there. And so it's possible at least some of these systems may be magnetically produced. This is unclear at the moment. A clear planet detection among the work that's being done is this famous PDS-70. This was advanced and the paper's written here in Heidelberg at MPIA with many international collaborators, which clearly shows the presence here of 2 planets, fairly massive Jovian planets here at 20 and 35 astronomical units. H alpha is a signature of emission of accretion, hot gas will emit. And this is what astronomers use H alpha emission to detect. So these are accreting, and we also see them here emitting by sphere observations in the mid-infrared. What about composition? How can we connect the composition of a forming planet to what we'll observe later? So this simple but very illustrative diagram by Karen Oberg and her collaborators illustrates very nicely what the game plan here is. Consider the C to O ratio, the ratio of elemental carbon to elemental oxygen, say you observe in an atmosphere of a planet. If you consider the gas out of which this planet is formed, if the planet formed inside of the water ice line here at a couple of astronomical units, then it will typically have the composition of that of the sun, the element abundance ratio. If the planet formed beyond the water ice line in this region, then you see that the water freezes out. So the oxygen content in the gas drops, C to O rises, and the solids, in fact, get a lower C to O ratio, while the gas phase gets a higher one. A planet's formed out here, as an example, with the condensation of CO2 out, a lot of the oxygen then moves out of the mixture, and we see that the CO ratio goes up again towards unity. Very far away beyond these ice lines, then the solids are left to carry the solar C/O ratio. So if planets stay in their place, measuring C/O in the atmosphere is akin to determining roughly where this planet may have accreted the bulk of its material. And there hangs this story. The kicker is that planets migrate. They don't necessarily lodge at one point, they move, as do the pebbles and planetesimals out of which the solid materials are made. And that's what needs to be tracked down in theoretical models. Continuing with outflows, the beautiful JWST image here of this classic bipolar outflow region with its accretion disk here obscured in this still enveloping envelope is an illustration of an outflows that occur in most, if not all, young stars, from brown dwarfs to massive stars, are all accompanied by the formation of disks and their outflows. This star is no exception. And in this infrared observation, you beautifully see this disk here. This is not a nice, smooth, regular structure. There'll be filaments flowing in here that will be part and parcel of the disk formation that's going on in this early phase within a few 100,000 years or less of the birth of this star. Outflows are active right away from the get-go. People have worked on outflows theoretically for a very long time, since the early 1980s, through greater degrees of sophistication. And it's a wonderful thing for a person like myself who worked on this in 1980 when I came to Cambridge as a young postdoc, first working with Colin Norman. There wasn't even an idea that there was a disk around in those days. Disks were discovered in the 1990s through infrared observations. The outflows for jets were measured in MPIA by various workers there. Christian Fent here is a theorist that's worked on the theory of outflows for a very long time with simulations, as I have. And it's a wonderful thing indeed that these outflows have now been resolved to their source. So both ALMA observations, shown here, show the evidence of a disk and a rotating outflow, red and blue shifted lines here, indicating a rotating outflow. From that, you can measure the amount of angular momentum that's being extracted from the disk. And that's about 60 to 70% of the angular momentum that needs to be removed to form the star. These VLBA observations in this source here are masers that are from this massive star formation that trace, move in a helical kind of a pattern. And this paper by Moscadelli et al., just recently published, links together with the theoretical work to show that there's a resolution of the acceleration region very close to the disk out to 10 AU. There's a disk wind that encompasses a wide region of what will be the planet forming region in this source. So physical processes in disks, well, it's complicated. To say the least. Here's a nice compilation and recent review paper. Just a few things I'll touch upon here. Let's talk about, as an example, the dust. We have the presence here of ice lines and various places where dust can accumulate, in fact. The formation of planetesimals by a so-called streaming instability, in which dust can quickly go from pebble size to objects 100 kilometers in size, is an instability operating to form planetesimals. The gas is distributed. The gas may be pushed open in gaps of the planet forming here, but its distribution is different than the dust. The dust is very more active in radial transport and losing its angular momentum through drag effects, and can gather and be forced into rings, in fact. So gas and dust distributions are not necessarily the same. There's a variety of turbulent instabilities that are occurring, apart from magnetic ones that I'll talk about in just a moment. Prominent among them might be this vertical shear instability that I'll mention in a moment. The MHD processes, you see the turbulence outer part of the disk, but in the inner regions where there's a strong outflow, turbulence is not present. So you have a laminar flow through those regions, and that will affect all of the physics that's been developed for how planetesimals and other things form, as I'll show you in a moment. First, the theory of accretion disks as developed by Shakur and Soniev in the early 1970s was the going model for how most, if not all, accretion disks worked, from AGN disks to around black holes to protostellar disks, etc. The idea is that angular momentum is transported radially by a turbulent stress. The turbulence in 1992 was shown that a so-called magnetorotational instability arising from the fact that weak magnetic fields threading a Keplerian disk are intrinsically unstable. The point here was first observed by Chandrasekhar, who noted that a stable distribution of angular momentum in a disk means that angular momentum increases outward, specific angular momentum. For magnetized system, that's changed to an increase of the angular velocity being stable going out. Keplerian disks have a decreasing angular velocity going out, therefore they're intrinsically unstable. Does this manifest itself as full turbulence? Simulations I'll show you in a moment suggest that this rotational instability is damped strongly, leaving only these weaker forms of instabilities present. If you have a disk that cools almost instantaneously, or hardly cools at all, or in an intermediate regime, the value for the kind of turbulence amplitudes expected may be from 10 to the minus 3 at top value to 10 to the minus 4 or even less. That is a very, very important result, because at those low amplitudes of turbulence, you cannot transport the amount of the accretion rate that's observed to fall onto young stars by that low level of viscous stress. Okay? That's the point. You need something else. And that something else would be the disk wind. So here's a comparison of the way the two general theories work in their extremes. If you have a disk wind, then as you're carrying angular momentum, there's a Maxwell stress on the surface of this that extracts angular momentum from the flow, giving you an advective flow. Material just constantly moving inward. The angular momentum goes out here. In a turbulent model, the angular momentum is transferred to particles by viscous coupling to the exterior part of the disk, which expands. This is where the angular momentum goes, driving most of the material inwards. So the overall surface density of the disk here, it drops somewhat just out to this expansion effect. Whereas in this disk wind effect, the column density is constantly being increased as the disk shrinks. That difference in column density has significant effects on concentration of solids and therefore on planet formation. So there are strong observational papers now by a variety of different authors and different techniques, which have indicated that turbulent alphas here, a limit of 0.007, the very sharpness of disk ring of rings that we see. If you have too much turbulence, the ring will spread out. So taking the observed width of a ring, you can put a limit of about 3 times 10 to the minus 4, as Kees Dullemont and his collaborators did a few years ago. Survey recently between a wide variety of observations and models indicates that alpha is in this kind of a regime for the turbulence. So these observations, together with the disk wind observations I show you, make a clear scientific case for how angular momentum, at least in the inner regions, 10 astronomical units and inside of that, must be moved. This is huge progress. How does a disk wind work? It's a lever arm. It's Archimedes' principle. A magnetic field in a rotating object enforces the co-rotation with the rotor out to some distance. So let's say, take this foot point of this field line here. It's a distance r0 where it comes into the disk from the axis. Follow this along and you see we come to a point here at which co-rotation can no longer be maintained. That's the Alfvén surface. The ratio of RA here to this R0 is the lever arm. The longer I make that lever arm, the more angular momentum can be extracted. In fact, calculations, ours and many others, show that that lever arm is a factor of about 3. So that if you balance the torques, you say the angular momentum carried off by the wind is extracted from the disk. You set up that theoretical calculation, you'll find that the ratio of the wind mass loss rate to the accretion rate typically is about 1/10. And this has been backed up by recent observational surveys by Watson and Pascucci in a recent review. They are around this kind of a range. So magnetized winds are incredibly efficient in extracting angular momentum with a minimal loss of matter from the disk. Here is a simulation, by the way. How you get a jet flow is that beyond this, the mass-loaded whip, which is the field line, kind of falls behind the rotation rate and coils up in a toroidal field, which exerts a pinch stress that focuses the wind here. So this is a simulation by Jan Staff, and I was on this team here showing jets going out to 100 astronomical unit. Red and blue here is the co-rotation, is the rotation of the jet itself that you can measure. You can talk to Christian Fent here for his very detailed 3D simulations that show similar effects. So the paradigm shift theoretically started here. Theoretically, quite apart from the observations, but from first principles. You consider a weakly ionized plasma, very weak. The ionization is from X-rays from the star. The ionization fraction can fall to 10 to the minus 13, 14, something very low. The coupling, if you have a magnetic field threading through the disk like this, the coupling is very tenuous. The ion-neutral collision frequency is rather low. That means that effects like ambipolar diffusion, which come about the slipperiness of the magnetic field, it's coupled directly to the ions, but that isn't very well coupled to the neutrals, so you have drift of the magnetic field, and that means that the MRI will be effectively damped. It kills the growth of that magnetorotational instability in the weaker part, in the upper layers of the disk and further out. On the midplane, where the planets form, then the densities and conductives are such that in a wide range, and here there's an absolute dead zone where ohmic losses kill the MRI instability. So these were the non-ideal MHD simulations worked out by this set of authors here, and that what they moreover showed is that all the MRI is killed, a disk wind is favored, is launched. That's the way the angular momentum is removed. So from first principles of non-ideal plasma physics, you can deduce for the ionization conditions here that one must go over from a turbulent, at least magnetized turbulence, gives way to a disk wind. Torques on planets, we're now going to switch gears a little bit to ask ourselves, how do planets move? Now, there's been many speakers on exoplanets here, I'm sure, but just in summary, a planet will raise a wake on a disk. They're one-arm spiral to the interior and to the exterior. These pull back on the planet in a back reaction, tugging it, extracting this wake here, pulls back on the planet, and therefore driving it inwards as it extracts its angular momentum. This wave pulls forward on the planet, speeding up, pushing it outwards. Difference between those two torques is called the Lindblad torque. And calculations show that that's generally outward motion of the planet. Close into the planet, much more complicated physics takes place. Think of the three-body problem. This is just your first year, second year physics three-body problem. We're looking at the co-rotating frame planet, star in the center here, looking at test particles, exterior to the planet far away. They're just moving in one direction, and the inner first, they're bypassing the planet. Here they're falling behind. In this co-rotation region, we have the gathering of material here. Now, if I put a density fluctuation here somewhere, because particles are librating around this loop, around this horseshoe, any density fluctuation will be smeared out in a libration timescale. So if you need a density fluctuation to tug and pull on this planet, it's gone in that time. To replenish that fluctuation by, say, viscosity, viscosity pushes material inwards here, and from this side, on both sides, pushing material in, depending on the density gradient, depending upon the temperature gradients. You can deduce that on this viscous time scale, you could maintain a density fluctuation. You can pump angular momentum into this region. So you will get a maximum co-rotation torque that tugs and pulls on this planet, generally pushing it outward, if these two time scales are comparable. That was first realized in these fundamental papers a number of years ago, and that gives you an outward co-rotation torque. The planet itself, when it's massive enough, in a viscous disk, you can compute that the gap opening mass, when you have a massive planet large enough so the tidal torque exerts on the disk, is greater than viscosity, which is pushing material back in. The ratio of the planet mass to the stellar mass depends on your turbulence level. Kill the turbulence, and almost any planet can open a gap. As an example, if you make this 10 to the minus 4, it would be about a Neptune mass planet that would open a gap in the disk. So once again, how turbulent a disk is important in a very fundamental way, because once you open a gap, you start killing the possibility of feeding the planet with more accreting gas. So just finalizing my review here of planet formation theory, to grow a planetary core, we can either grow a small core by pebble accretion, masses of centimeter size pebbles, or take pebble accretion and build planetesimals, 100 kilometer size bodies, to build up cores, oligotic cores, which then gradually, as they become more massive, this is a very rapid process. When the core becomes comparable to gas envelope, as we start gradually drawing down gas, when these two quantities become approximately equal, gravitational instability can take place, and we grow a giant planet. I'm now going to switch into the recent research that I've been doing for the next, I think I have 15 minutes left, on several aspects of this story that are important for my story. First is the bifurcation. What do torques look like on planets when we put them in disks? And how do planets move in response to them? This is a paper of Jess Speedy, my undergraduate thesis student, the first author here. And in this calculation here, we're just taking a disk model, which is Chambers disk of 2009, a self-similar model that well matches observations. I'm calculating here the Lindblad torques and the co-rotation torques, which depend only on disk properties. Okay, it's a function here of planetary mass. And the red shows is anything as torque that's directed inwards. The purple line here denotes anything up here will undergo type 2 migration. So if I'm sitting in this radius in the mass, all these planetary masses here will undergo inwards migration by Lindblad torque, and here we'll have type 2, and so on. If you look at the co-rotation torques, that's blue and that's outward, they have a peak value, a maximum that then falls to 0 as we go to this regime where high masses, where we say the torque is saturated. The turbulence doesn't fill in the disk and in the co-rotation region, and the torque so-called saturates in this region. If you add those two torques together, you get this diagram, the total torque. And here in the structure of the disk, we have a dead zone where the turbulence is very damped down, no MRI whatsoever. A little bit from the other instabilities left. So you see that the gap opening occurs at very low mass. When we get our active region of turbulence here, you see that we jump up in this torque diagram. All of this is type 2 migration up here, and this is type 1 beneath it. Places where the net torque is 0 are planet traps. So a planet can reside there and move along with the disk slowly. It won't undergo rapid migration. If you have a low viscosity region, you see that this region is down from this one. I've located 3 kinds of traps here. This is where we have an ice water line here. This trap there's a dead zone here. So there's the edge of a dead zone is another trap. And this wide region is where we transform from the viscous heating of the disk to heating by the central star. And that leaves a wide transition region here. So if we ask ourselves then, how does a planet move in such a configuration? That's shown there. So here we're following a planet moving on a planet formation trajectory. It's been caught and resides in this trap here out at 30, 40 astronomical units. It's gradually being brought back as the disk turbulence, the column density drops, the turbulence drops away, the viscous region shrinks, and this transition trap moves inwards like this. This is a profile of the peak of the co-rotation torque shown here, and where the planet lodges with respect to that peak as it migrates. And if we now show you a whole collection of trajectories for the high and low viscosity cases, you'll note that in the high viscosity case, planets rapidly move inwards before they're caught here. In the low viscosity case, this co-rotation trap, this transition trap here, is lower in mass. So planets, before they migrated inwards, are caught and wafted outward to tens of astronomical units before they are brought back. So low viscosity systems can pump planets out to large radii. High viscosity systems become compact as to where their planets are. Disk viscosity then can probably control the structure of planetary systems because of this. Those few systems that manage then so this is a function of mass. If I increase the mass somewhat, here's a low mass disk in blue and a high mass disk in red. You'll see the effect is more pronounced the more massive we make our disks. So here's the explanation for Nick and van der Mel's result. You have few massive disks. In those massive disks, that's the same frequency as of Jupiter's. Massive disks should have lower viscosity. The viscosity is dependent somewhat on this magnetic coupling, which isn't there for more massive systems screen the ionization that creates the MRI turbulence. So we've proposed that this is an important mechanism, this bifurcation. And just some analytic theory that backs these results up. You can compute the mass at which this co-rotation torque peaks, which we've done here, and derive an analytic expression, which again shows the dependence upon the viscosity in your disk. If you do this question for wind torques, which was done in the paper by Kimming and Keith Stilmont and Clay here, you find that with a high enough mass loss rate from the disk, you can drive planets outwards. The physics is somewhat the same. Here, rather than instead of pumping angular momentum into this region by viscosity, here what you have is an advectant flow. That material is being driven inwards by the disk wind on some wind timescale. So what matters is if these two timescales are comparable, but within a factor of 10, then once again, you have a strong outward torque. And in our paper, we calculated what the co-rotation mass, what the peak mass is, dependent on the strength of the wind. Winds are very strong when planets and stars form first. So we're expecting that as a disk evolves and its wind strength changes, that will affect the population of how planets are moving within them. I'm going to quickly go over population synthesis models then to connect with population planetary compositions in this other paper here now. This is with my student Matt Alessi. And here we put together then models using mass and angular momentum driven by disk wind and turbulence, following published papers of how to handle disk wind dynamics, those authors there. Putting that together with heating by viscosity in the inner part of the disk and stellar radiation on the outer part, as I showed you. We have equilibrium chemistry. So we have detailed chemistry calculations in the disk itself to tell us exactly where different ice lines, et cetera, are. And with this, we do a calculation. The wind strength we relate to the accretion rate by this standard scaling that I showed you before from theory. And then we look at the properties of populations that we get. I'm going to skip this. In this calculation, we've done over 3,000 models with chemistry included in all of these disks. We do, in a population synthesis, we do stochastic variations of the observable quantities. Disks come with a variety of column densities. They observed with a column range of metallicities and lifetimes, and we take these from the observations. The 2 points of theory that we introduce, and only 2, are that we say that the maximum mass of a planet can occur is related to the gap opening mass. Now, everyone thinks that's true, but the exact factor here, there's not general agreement on. So we're handling this as a variable. And we're assuming, for all the reasons I've given you, that the turbulence strength from system to system can be different. Disks are in different environments. They're in different stages of ionization. So the alpha turbulent component would vary. So with those assumptions, here are the growth of a planetary population. These are following planetary population formation tracks. You can read our papers to how those are computed. Here we're using planetesimal accretion, not pebble accretion. And we're showing the end results. So this is the hot Jupiter zone. These are the warm Jupiters. Here are the super Earths. And I'm just about almost finished. I'll run that again if I can. Yes, the time is shown up the upper right-hand corner. And you see very quickly that the source of planets in the hot Jupiters are actually from the dead zone. They get there quickly. The ice, ones that form primarily around the ice line and blue tracks there, form somewhat later. And then we have a gradual appearance in the more long-lived systems of the super Earth population occurring later. These are ones that have been cheated of their gas. There's a variation of time scales for the amount of time that a disk has its gas before it's dispersed. And the super Earth population happen to be those that don't get quite enough advanced in their mass to still have enough gas around to attract, before the disk dissipates. So here is the correspondence with the final results here. So you were a factor of too many hot Jupiters, but too few super Earths. Our populations here are pretty much okay for the warm Jupiters. There's reasons we can expect the hot Jupiters are feeding off. There's not as many super Earths as there should be. They're ending up in the hot Jupiters. There's a reason for that I don't have time to get into. But here's the way the radii, the mass radius relation looks for our planets. This is before we apply photoevaporation to the atmospheres. And this is after photoevaporation has taken place. This is the mass radius diagram. The gray are the observation points. And these are the results from our thousands of models that we've run, coded by the different where they are, what is a heat transition, ice line, or dead zone type of a region shown in here, and showing the various tracks. So many of them are indeed lying along this Earth composition track. And then we are getting the upper envelope of the observation. So we need to fill this in. I've come to the end of my time, so let me just summarize. My summary is that the observations, disks, winds, weak turbulence, theory, and simulations now are all converging to a new paradigm. That paradigm is a disk winds dominate disk evolution, and probably planet formation from what I've been trying to convince you of today. Our best fit, it still has its wrinkles to be worked out, of course. The dominant disk wind is carrying off the bulk of the angular momentum with disks with a wide variety of turbulence in the populations that we're seeing. We have a decent fit to the mass radius diagram. I didn't show you our fit to the CO data, which is fairly reasonable. I would say that the tight connection to the observed population of disks is that the mass of disks we're expecting to be lower viscosity, and that fits very well that lower viscosity planets in lower viscosity disks are pushed outwards to large radii before they return. And that difference in the size of the population with low alpha versus 10 to the minus 4 versus 10 to the minus 3 alphas may be responsible for that difference we're seeing in these populations. And that's open to observational testing. So with that, I thank you very much for your patience.
Thank you very much, Ralph, for these insights. Would not believe that one could do so much with what is still quite rudimentary data, but which is increasing in sophistication with time. So I'll invite questions from the floor and from the Zoom audience.
Hi, a quick question about the diagram that you presented of the disk wind. I think was from your paper. Maybe you can go back, hopefully, to that slide.
Sure. Let me...
where you explain the basics. Actually, I have relatively basic question anyway.
I think I know the one that you mean. So long way back here.
Yeah, after that, exactly. So that Matt and Pudritz 2005. So my question is this RT, right, is the radius where magnetic accretion occurs, right?
Onto the star, yes.
Yes. So do we have any good estimations for that radius from any kind of observations or even theory, which is more detailed to what I have done?
Well, the theory has been long worked upon. It started in the theory of X-ray pulsars, et cetera, of X-ray sources. That's the magnetospheric radius. So what you're balancing and to calculate that radius is the magnetic field stress in that dipole field against the Reynolds stress of the accreting plasma onto it. And where that stress of the magnetospheric field exceeds the accretion stress, then in that picture, then you break the inner part of the disk there, and matter then free falls along these field lines like a roller coaster ride onto the star.
So for doing this for a protostar, we will definitely need a model for the magnetic field, the dipole magnetic field from the protostar.
People have measured field strengths for such stars, and there's a significant number of publications upon that. There's measurements of the accretion flow. If you go to Nurio Calvet and Lee Hartman's papers, over many years, there's various types of emission lines that are produced by the accretion shock onto the star. And it's from that we know what the accretion rate is onto a star. So that's a measured value. M.A is known. So I didn't make that up when I was saying that it's not a theoretical thing, but it's an absolute observation.
Yep,
thanks for making the point.
Thanks a lot.
Keith Dullemon has a question.
Yeah, thanks, Ralph, for his wonderful talk. I've long been puzzled, or it has long been going through my mind the following conundrum. If you have an accretion disk that has a dead zone, that is usually the regions close to the midplane, whereas in the surface layers, there is still enough ionization usually to have MRI. But at the same time, if you want to have a disk wind, you need also the magnetic field to be anchored somehow in the disk. So if you would completely switch off the ionization, then you would not anchor the field lines. Whereas if you have enough ionization to ionize the surface layers, then in the surface layers, you could also have MRI. So I'm always a bit, so what is your take on that?
So that is that's exactly the revolution that's taken place in the modern simulations, of which this work by Albert Gressel is one, but of which there are a number of groups that are working on this. So what you see I'll just walk over here, the well-coupled region in which there's ideal MHD essentially is occurring at about a layer like this, okay? The MRI instability is being quenched also in the surface regions by ambipolar diffusion. That was the neat result. People had always thought, well, sure, the ohmic dissipation is so strong, the ionization at the plane is so low that yes, we'll kill it there. But there was the idea that flow could occur, just by turbulence in the MRI turbulence above that. And that's what Stone showed didn't occur. That it had to be stuff flowing out this way, angular momentum went this way, that even there, the MRI turbulence is significantly damped. So there's a region here, field lines, they're not drawn by this paper, but you see the outflow being accelerated along field lines here. Inwards here, there'll be a layer right in here above the midplane where the accretion rate is flowing onto the star. That's allowed by the non-ideal MHD. You can cross field lines to some degree if you don't have complete coupling. So you're not completely anchored, but you're anchored just enough to allow some flow to go through you and take the angular momentum out. So it's an interesting balancing act. I don't know if that answers your question.
Hi, Ralph. I have a question. Do we have some statistics? What kind of wind is driven from disks that form planets? I mean, you have seen these pictures of the disk forming, planet-forming disks, but we don't know what kind of wind they drive. So do we know that from observations?
So we do know something about wind mass loss rates because for years, people have using Hubble Space Telescope observations to look at jets from young stars. Now, jets are quite common. I mean, you were part of a group at MPIA. And so
I'm not asking about this planet-forming disk. So if you see a disk that has planets inside, this kind of things we see from ALMA, do we know for that exact disk what is the wind mass loss rate?
Yeah, actually, HL tau is a good example. Okay. HL tau is one of the first sources to winds measured, at least in the way we used to do things with CO flows and that. And so, yes, there is a wind mass loss rate for HL tau. I don't remember it off the top of my head, but there is a nice outflow there.
So towards the end of your talk, you were mentioning this population studies, and you're mentioning some alpha value, and you said it's varying. Is it varying in time or in space? Or when you quote alpha of 0.07 or so, is that a constant value across the disk, or is it a typical value? Or
so across the disk, alpha is changing. So in the dead zone, the turbulent alpha is very low. Where we get to the point where the technical thing that you do is you compare the growth rate of MRI to the damping rate by whatever mechanism. And so you will find a place where the MRI, which is the strongest version of turbulence, will occur. And that's the edge of the dead zone. Now, as the column density of the disk drops, the depth of the ionization changes, so that dead zone shrinks with time. So that what was once a poorly coupled gas does now become coupled as the disk column density drops, as the disk evolves. So yes, at any one time. So what we've modeled is we've said let alpha be constant, like in a turbulent zone and a different value, but we have put that into account. And our models that I didn't show you have a constant wind alpha, if you like, but a varying turbulent alpha as you go through the disk because of this effect.
If there's nothing from the floor, could I just ask a very, very naive question? Sure. The migration of the planets, this would, I would guess, be accompanied with a change in the eccentricity of the orbit. So is there some sort of observational link between eccentricity and position on these diagrams on the semi-major axis and maybe even composition, which could be used?
That's a great question. In a full version, if one gave a few lectures on this, the great missing diagram here is the eccentricity of the orbits. And that is a very, very interesting problem. I'm not sure that any one of the physics that I've talked about here has much to say about that, save for the fact that when a planet's in a disk, eccentricity tends to be damped quite strongly by this disk-planet interaction. So the idea is that eccentricity can grow. One way that eccentricity can abound was once the disk goes, then you're left with a planetary system. Those planets now aren't necessarily going to be in their final orbits. They will be interactions between planets, and processes like that may start to affect the eccentricity. As to how far planets will move because of this, my former student, Soko Matsumura, who's an expert on dynamics, in a paper by Chatterjee et al., they reckon that you might move by a factor of 2 in disk radius when you take into account this kind of effect. So it's not huge on these scales, but it's significant. And there are many questions about the origin of eccentricity that are still not solved, I would say. This is a great problem for dynamics, but I feel that what you come out of, once you come out of one of these models, if we ever get this right, and you remove the gas, then it's an interesting dynamics game.
So thank you, Ralph. Thank you very much for this very incisive and illuminating picture of the future knowledge we are gaining from all these planets, these systems. I wouldn't have thought it was possible, but you have really showed us that it is. Thank you very much.